Okay, so now we have the theorem proving session, and 4 speakers whose pictures were just flashed up by Jeremy Avigad, Alex Davies, Amaury Hayat, Melanie Wood from our own math department. And please take it away.
Thank you. Can you hear me well?
Yep.
Good.
Perfect. All right, so thank you very much. Thank you to the organizers, and in particular Mike, for the invitation. This was an amazing program, and with Jeremy Avigad, Alex Davies, and Melanie Matchett, we're going to talk about the Theorem Proving Week. So as you guessed, this is a joint talk, so I can't really tell you what's going to happen in the talk. I can only tell you in which order it's going to happen. So I will start, then there will be Alex, and then Jeremy, and then Melanie. And because I'm given the opportunity to start, I'll start by saying that proving math theorems with computers is not something new. Even in pure mathematics, it has been there for a long time. My favorite example is this conjecture by Euler in 1769. So Euler thought that if there exists k plus 1 integer, such that if you put the first k to the power n and sum them, and it's equal to the last one to the power n, then k has to be larger than n. So he wasn't able to prove this, and this remained an open problem for almost 200 years, until Lender and Parkin arrived in 1966, and they solved the problem by essentially the most silly way you can imagine. So they tried many possible combinations with a computer, and they ended up with this. So you see that you have 1, 2, 3, 4 integers here to the power 5. And so if Euler's conjecture was true, then 4 would be larger than 5, and we all know it's not true. So this was a counterexample and a new mathematical result. But most importantly, this was also the only paper that I know of that can fit on a single slide. Now, there are, of course, much more recent examples, like the proof of the Keller's conjecture, or the last case that was remaining. So this is a proof that can be reduced to many simple cases to check. But the problem is that many is really far too many for human, and so these researchers managed to solve it with a computer. But the proof at the end of the day is so large, you're not even asking yourself how many pages is the proof, you're asking how many gigabytes is the proof. And in this case, the answer is 200 gigabytes, so it's around 10 times Wikipedia. So it's something that, at least in this line of proof, could not have been done without a computer. So computers have been used to prove theorems for a long time. And with new tools such as Charton's int-to-int or pattern boost that you'll probably see in the next talk, this is not going to stop here. But in these examples, the computer is helping as a computational tool, so a very useful tool, but the humans are still doing the reasoning. And so one question that you could ask yourself is, can an AI apply reasoning steps and prove eventually even statements on its own? So there are reasons to believe, mostly because in the last decade, there were huge progresses in machine learning, in particular in language models. So we've all heard about ChatGPT. I mean, most of us, I guess, have heard about the transformers in 2017. So language model on the one hand, and also reinforcement learning, essentially learning by trials and error. We can think of playing with Atari in 2013, or of course, AlphaZero in 2017 and the subsequent work. So if you were to train an AI to prove theorems, the first question you should ask yourself is, which environment are you going to choose to work with? Essentially, in which language are you going to interact with the AI? A natural first answer could be, I'm going to use informal language, like French or English or whatever human idioma that I can find. But this has some problems. The main one is that if you train an AI to give you a proof in French or English, let's say English, it's going to give you a proof of this exercise, for instance, and then you will need to check this proof, and you can't do this automatically. So you will need to ask a human to check this proof, and this can be a problem if you're training an AI, because essentially you will need to do many, many checkings. The second problem is that if you use, for instance, reinforcement learning on this, where the neural network is going to try to maximize the reward, there's a possibility that you're actually teaching your neural network to cheat. Because if it's a human checking and you try to reach research level mathematics problem, then at the end of the day, it might be easier to fool a human than to actually perform good mathematics. So fortunately, there is an alternative that is using a formal language. So Formal language is something that you will hear more about in the rest of the talk, but it's essentially a language that is meant to be read in some sense by a computer, so it looks more like code. And if you manage to write a proof in a formal language, then the computer can verify it automatically, meaning that you can have an answer, a kind of guaranteed answer, yes or no. So there are still challenges. One that we are going to discuss soon is that there are very few data available in formal languages. For instance, this is written in Lean, and in Lean, the main mathematical library has around 150,000 theorems. So this is a lot for human, but not much for a language model. The second challenge, and then you'll hear more about this in the rest of the talk, is that these languages are often made to verify a solution rather than finding one. And you will see in the rest of the talk how it matters. All right, so now that we know we're going to work in formal language, if I were to ask you, can you design an AI to prove a theorem? I guess the first thing you will try is to try to train a transformer, a kind of GPT-like model to prove a theorem. So like this, so you give an exercise, it goes into the language model and gives you a proof. This is something that was tried in 2020 by Stanislas Polu and Ilya Sutskever when they were both at OpenAI. So they developed what they call GPT-F. F stands for formal. And to understand a bit more how it works, we need to essentially try to understand what there is in ChatGPT. So there are many things, and I'm going to forget most of it. I'm going to focus on the autoregressive transformer. Let's assume that you have a neural network that is trained to autocomplete a sentence. The way it would work, the way this autoregressive transformer would work is essentially take your sentence. Thanks to the training, compute a density of probability of the next token. So let's say it's the next word. And then sample according to the density of probability, and then you get a new word. Then you put it back into the sentence, and you start doing the same. So this is the autoregressive fashion. And at the end of the day, the neural network is at some point going to output something saying a token that says end of the sentence, and then it returns your sentence. And here, because this is a quote from a movie that is at many places on the internet, it's likely that if you train your neural network on the internet and you start to have something that looks like the quote, it will probably converge to this quote. So you can try to do the same with math. So let's take a math statement. You will have a neural network after training on whatever data you have that will compute a density of probability of the next step of the proof. Then you can sample the step of the proof, put it back in the stack, and do the same again. And you hope that at the end of the day, the neural network will say, okay, now I sample something that says this is the end of the proof, and this is my proof. So this is the first way of seeing the thing, but because we are working with a formal language, we can do something slightly smarter, which is after I sample, so I have my statement, I sample the first step of the proof. And then before doing this again, I can apply this to the statement and see what is the state after. For instance, here, this is still written in Lean. If you have this, that is essentially cosine plus exponential is smaller than 1 plus 2 exponential, you can apply this theorem, and this is what you have left to show. So you can do this, and at the end of the day, you hope that you will have nothing left to prove, and if you have nothing left to prove, you don't even need a neural network. You can just say, this is the end of my proof. So you can be optimistic about the fact that it works, because, I don't know, maybe because ChatGPT is very good. You could be pessimistic, just because, you know, you're essentially trying to learn to reason by looking every time at just the next step of the proof. In any cases, this can only work if you have enough examples. Enough meaning sufficiently diverse and sufficiently numerous. And this is precisely a limitation because, as I said earlier, we don't have that many data, that many mathematical proof in formal language. So there were many subsequent improvements and variations. Lindojo, for instance, tried to train a second model, a retriever, on the library to suggest relevant theorems to apply to the language model before it takes its decision. Lin Lama tried to see what could happen if you use a better and maybe bigger large language model. What's the good trade-off in size? And other approaches tried to tackle the lack of data, either by using additional data gathered on the internet, that's for instance Lemma or internal M2, or by using what is called automatic formalization. I won't say much about it, but it's essentially taking a statement in English, for instance, and translating it in Lean. That gives you additional data. or even synthetic data that are generated with a generator that you design. So this is, for instance, what DeepSeek Prover did. And in all these approaches, at some point, they were confronted to the question how to go further. And for most of these approaches, the answer was to use some kind of reinforcement learning. So before going to the next slide, I'll just note that all these papers are from 2023 or 2024. So you see that this is really a field that goes very quickly. All right, so the second approach is essentially reinforcement learning. So it treats, in some sense, mathematics as a game and try to explore the possibilities with reinforcement learning. The motivation behind is, of course, one of the motivation behind is, of course, AlphaZero, the AI that learns to play chess and gets in stealth and becomes much better than humans after a few days of training. And the game you wanted to play is the following. It's the math game. You have a statement you'd like to prove. You apply a theorem, for instance, so that you make a move. Then you have the assumptions to show. And then if you manage to, at the end of the day, to be in a state where you don't have anything left to prove, then you won. So two open source examples of this are HTTPS that was made in 2022 and Able, that's essentially the version of 2024. And the goal is to essentially see your proof as a tree, a very large tree of all possible proofs. You start with one node, that is a statement you'd like to show. And then every branches, every edge is an action that you can take. So because there are so many actions you can take, this is a very dense and very large graph. And you try to explore this graph of mathematical proofs in a smart way. And whenever you manage to prove something, you use it to keep training your neural network. So this is essentially in 20 seconds how this would work. This is where the reinforcement learning comes into play. And the strength of this approach is that it gives very good results, even with limited data and somewhat limited computational cost. So natural question is, what can be done with more involved search and more data? And on this note, I let the floor to Alex.
Awesome, thanks, Amaury. I'll just see if I can share my screen. Awesome. So I thought that was a great overall intro into this intersection between formal languages and machine learning. And I think that I will emphasize further the point that Amaury made where, all these papers are coming from 2023 and 2024. I think there's a lot of interests now at looking at the intersection of formal languages and large language models, especially because they're very complementary in nature. Large language models, you don't have necessarily good ways to judge correctness, as you mentioned. This is something that Lean and any of the other formal theorem proving languages do give you, this idea of groundedness and being able to tell that a proof is actually formally correct. And this is really helpful in the context of reinforcement learning, because in reinforcement learning, you need to have this grounded reward signal to tell you whether or not you've done something good, because you're going to be generating a lot of proofs, many more than a human could ever mark, or we want to put anyone through that. And so Lean really gives you this nice environment to do this. So at DeepMind this year, what we did was used a combination of Lean and large language models to kind of compete in the International Maths Olympiad. So not the actual competition with the students, but on exactly the same problems just after the students had finished competing. We had a system based on AlphaZero, which I can go into slightly more details on, that was trying to solve these problems. And I think the experiences during this competition really led me to be interested in this idea of maybe not just using Lean as a theorem proving language, but also as a forward reasoning engine as well. So I feel like this slide is probably largely unnecessary for everyone here. I'm sure everyone knows what the IMO is, but this is an example of one of the questions from this year and its formalization into Lean. So as you can see for this problem, The formalization is pretty clean. It's quite short. This is not always the case, depending on the problem and the category of problem. The formalization of statements can be quite difficult. This one here is quite easy. I think this kind of took everyone by surprise. It was kind of roughly expected that it would take another couple of years probably to reach a decent standard at solving IMO level problems, because they are fundamentally quite hard problems. But this combination of lean and very effective machine learning and tree search really outperformed, I think, all of our expectations, including mine. Specifically, the performance that we achieved was reaching we got 4 problems formally verified as correct, which placed us this year just at the lower bound of the silver gold cutoff. And obviously entering in a formal language is slightly different than what human competitors would be doing. But here we consider ourselves correct if we have a fully formalized proof that compiles to correct and incorrect otherwise. And as you can see, we answered all of these 4 questions correct with I'll make a caveat that geometry was handled separately with a different system. So here I'm only talking about algebra and number theory. But we failed to solve either of the combinatorics problems for reasons that we're still going to have to try and figure out. But it certainly seems suspicious that combinatorics is also almost always quite hard to formalize problems compared to number theory and algebra. Number theory and algebra are generally pretty straightforward using MATLib to formalize. Combinatorics can be very difficult. And for the competition, we had human experts doing manual translations of the problems into formal statements. And for the hard combinatorics problem for P5, for the one that was hard to formalize, that took them almost several hours to actually get a formalization of. And fortunately for us, combinatorics wasn't P6. It was an algebra question. And here is the full proof that the reinforcement learning system found in the end, with the comments added by human annotations. And this was a particularly tough question this year. One of the things that impressed Tim Gowers, who was one of the kind of internal adjudicators, was that it did manage to find this quite insightful observation that's required to solve the problem, which, again, didn't really come from any general learning. This only came from the reinforcement learning agent trying to solve lots of IMO problems and trying to learn what kinds of things generally would be considered as, you know, observations that might help unlock this problem. So the overall setup for what the pipeline looked like was starting with a large number of informal problems, so problems in informal language, maths problems, you know, leading up to the difficulty of IMO level problems. And then during training time, using a large language models to translate the informal problems into formalized versions of these problems that we can then use as a curriculum to start training AlphaZero. So you then, once you start with a bunch of informal problems, this formalizing process can be difficult. So we formalize a bunch of different versions of the informal problem statement so that we're very likely to have at least one correct formalization of it. And there's often multiple different ways to formalize a problem, all of which are valid. So that increases the size of the data set from around 1 million to 100 million. And then you have this solver network, as Amaury said, learning to play this game of auto-regressively generating lean tactics, and then using tree search to try and explore this game state, to explore this game tree of moves that you can use to eventually reach a conclusion to the proof, a complete proof, which is the only reward signal that you need for reinforcement learning, which is that you finally, at some point, got a correct proof. But at test time, we kind of had this issue, which has been, I think, reasonably well understood by a small set of people for a long time, because many years ago, people were suggesting of the IMO Grand Challenge, having something solving IMO problems in Lean would be a really a grand challenge for mathematics and machine learning, computer science. But the framing of these problems has always been that there are two types of problems in the IMO. There are those which require a final answer and those which just require a proof. And it's about 50-50 split of these types of problems. And so for problems that just require a proof, this fits very naturally into Lean. You just have a formal statement that you need to try and prove. But many questions are of the form, find X such that it satisfies a number of criteria. And then your job in solving this problem is to both find the correct definition of X and prove that it's correct. So since we wanted to enter the IMO in a way that was as comparable as possible to what the task that the IMO actually represents, we decided that it was necessary to both figure out the answer and then prove that it was correct. And so the way that we did this was to essentially break out of the Lean formalism and have two kind of separate parts of the system here, where for this P1 question, we need to determine all the real numbers alpha such that a condition holds. And here we kind of take advantage of this current strength of large language models, so Gemini in our case, as well as Lean, and we use Gemini to try and reason through what the answer might be, so kind of credible guesses at what the right answer is. And if you've used any of the large language models, while they're starting to get good at reasoning, none of them are good enough that they could actually reliably figure out the answer to a question that's this hard. But if we can have it come up with a lot of plausible candidates for what the correct answer is, and automatically formalize these into the statements, then we can allow the proving agent to try and figure out which of these candidate answers are actually the correct one. And if we get to a formally correct proof, then we know that we've both found the correct answer and a valid proof of this. But while this was sufficient for us to do well in the competition, I think for me it really drove home this point that to use Lean as a system of reasoning, of doing mathematics, there's a lot more to mathematics that's happening than just formalizing a proof or proving a statement in a formal language. There's a lot of forward reasoning. There's things that aren't captured by this, but maybe just for the purposes of this talk, we're going to think about this. How do you reason in a forward manner to get to an answer? And while we can do this with large language models in an informal setting, I think it's a really interesting question to see whether Lean also provides maybe a really interesting way to do this too, which might lead to even stronger forward reasoning than what you can get away with in pure natural language currently. So with that, I think I'm passing over to Jeremy.
Yep. Excellent. Very good. Let me share my screen. Okay, so if, let's see. So if things are going well, you're looking at a browser with the 1965 IMO problem 1 on your screen. So if that's not the case, let me know. So during the week that the four of us were together in Cambridge, we had a good time talking about ways that one might train a model to solve problems that's better than guess and check. And what we were thinking about was ways of setting up the theorem proving task in Lean that would somehow cause a model or encourage a model to solve the problem and prove its correctness at the same time. And to think about how that could work, we did some experiments formalizing in Lean the IMO problem that you're looking at on the screen, and thinking about different ways that one could set up the formalization, and then again try to train machine learning to do something similar. So that's what I wanted to describe for you now. But first, I want to go over the problem because I think it gives you a very nice illustration of the differences between solving a problem and proving correctness. So the problem asks, us to determine all the x in the interval from 0 to 2 pi, such that these two inequalities hold. And as far as IMO problems go, this isn't a very difficult one. It's it's pretty straightforward. So the solution says it's going to look at the first inequality first. And the first thing to notice is that if you case on whether cosine x is positive or negative, so in the case where it's negative or even non-positive, the first inequality is trivially true, because the absolute value is always non-negative. Okay, so that leads you to focus on the case where cosine x is non-positive. Is non-negative. And in that case, you can do so. The solution has you square both sides, and then you calculate with the square of this thing, and you reduce it to expression. So you reduce the inequality, the squared inequality, to this thing here, which involves the absolute value of cosine 2x. And that suggests that you then want to split on cosine, the sign of cosine 2x, right? And in the case where cosine 2x is non-negative, you get, one inequality, and you just do trigonometric identities, and you can solve that. In the case where cosine 2x is negative, you get a different inequality, and you could use trigonometric identities and solve that. So that takes care of the left inequality. You figure out all the x's between 0 and 2 pi where the first inequality holds. And then you get around to looking at the second inequality, and then a calculation shows that it always holds. Okay, so the answer is the interval pi over 4 to 7 pi over 4. And so here are the notable features. So the first, and I think most striking feature, is that you only get the answer at the very end. It's the very last line, the very last phrase. It's the very last string of symbols in the proof. And so when we look at the lean formalization, you'll see that to state the theorem, you have to state the answer. It's the very first thing you state. So that's striking. So that you're doing this whole chain of reasoning, but you only know where you're going to end up at the very end. And not only that, once you're at the end, you don't have to bother to prove it, because the chain of reasoning has you've argued that this has to be the solution. Okay, so rather than giving the solution and proving it's correct, you're reasoning to get to the solution in such a way that once you get there, you know that it's correct. So we'll see that that's one striking difference. Another difference, interestingly, is the case splits. So here we split on the sign of cosine x and cosine 2x. And in each case, once you do the case splits, you reason about, where, if cosine is 2x is non-negative, you can reason about the intervals where that's the case. When I show you the formal proof in a moment, you'll see that it was actually easier to case split on the intervals. In other words, once you know that you're trying to get to this interval, it's easy to split up into subintervals and so on, and do the case splits on where x lies, right? So when you're solving the problem, you do the case split on things that will help you, simplify expressions. But when you know the answer, it's easy to say that, okay, when x is in this range, then we know that cosine x is non-negative, and cosine 2x is non-negative, and so on. So that's another difference. It's where you choose to do the case splits. Another thing that was interesting in the formalization is in the first split, you split on where cosine 2x is non-negative. And then you get the annoying thing is that in this case, the inequality is almost always false, except for, at the endpoints, at these corner cases. And these corner cases, then kind of reappear in the next one. And so proving the theorem formally, it's easier, it turns out to be better to do the case split differently, make cosine 2x strictly negative here, and then non-positive in case 2. Right, so that's another common thing. It's like once you know the answer, then after the fact, you can sort of think of more efficient ways to prove it. Another interesting thing is that the proof involved, once you're already into the first case split, you do a calculation. And then at the end, you realize that you want to do the same calculation again. As above, we can square it and have it be true, blah, blah, blah. you don't realize that you need to do this calculation until you're in the first, in solving the problem. You don't realize you need to do the calculation until you're, into the first case. But then you realize that the calculation doesn't depend on the thing you cased on, and you're going to need it later on. So that really, deserves to be broken out as a lemma or something that happens earlier on. Okay. And finally, the other thing that changed in formalization is, at the end, when you look at the right inequality, you realize that it's trivial. And so when you're proving the theorem, it's kind of easy and convenient to handle that first. So so here is the formalization in Lean. And so ICC stands for closed interval, close. So this is the closed interval from pi over 4 to 7 times pi over 4. And right up front, we define that to be the answer. And the theorem is that the set of x in the interval from 0 to 2 pi satisfying the two relevant inequalities is just that interval. Yeah, and so here, I mean, this is just now all the things I said would be different are. So this is the first calculation, the calculation that I said should be split out and put at the beginning. So, in the proof, we did that. This was the right-hand inequality, so that one there, that you dispense with quickly. And then having, once you dispense with it quickly, you're focused on the simpler problem where you just have, you're just trying to determine the x from 0 to 2 pi such that the left-hand inequality holds. And then, okay, so so by extensionality, there are two directions. You want to show that every x, in the interval that you gave in the answer satisfies the inequality. And conversely, if you satisfy the inequality, then you have to be in the interval. And, we just do that in steps. So for the first direction, we have to show that, for every x between pi over 4, there's the first conjunction is easy. Yeah, so the first, let's see. So so the first direction, you have to show that every x in the interval from pi over 4 to 7 pi over 4 satisfies the inequality. And so what we do is we do that by splitting it up into the three cases. You're either between pi over 2 and pi over 4 and pi over 2, or between pi over 2 and 3 pi over 2, and 3 pi over 2 to 7 pi over 4. Okay. And so, we split up on cases. And now we have three goals, the first one, the second one, and the third. And now in each case, we can reason about whether, cosine x is positive or non-negative and cosine 2x, right? So we just do all that reasoning, and then it's just a calculation in each one. And then for the reverse direction, that's where we have to show that if you're, so the converse holds, if the inequality holds, then you're in the interval. And we do that by contradiction. Let's see, namely, we show that if you're not in the interval, then the inequality doesn't hold. And again, at that stage, it's just a slightly fiddly, but straightforward calculation. Okay, so that's the formalization. And again, the proving process looks very different from the solving process. So now let me talk about, so we considered a couple of ways of kind of try to rewrite the proof. So one thing we talked about is that, as far as stating the problem as a solving problem, I mean, we can state it as a problem of showing that, there is an answer such that the answer is equal to the set that we want. Stating that way is a little bit unfortunate in that, kind of trivializes the problem. I mean, Lean can easily prove that. And if you just call the simplifier, it will in fact prove it by saying that, yeah, I can prove that there is an answer, that's equal to that set. Namely, that set is equal to that set, just by reflexivity, and we're done. But as Melanie pointed out, we can, from the outside, we can kind of constrain the model just to reject any witness for the existential quantifier that's not, sufficiently explicit as may be judged by another model. And so we consider that, if you did that, if you just kind of forced the system just to find good answers, how could it possibly reason forward? And so what I'm showing you with this experiment is kind of a way of reasoning forward that really is just kind of a translation of the solution that we discussed. So for example, when we say we shall deal with the left side of the inequality first, and then it's clear the left inequality is true when cosine x is non-positive. So that basically comes to the observation that, when x is in the range from 0 to 2 pi and cosine x is non-positive, then the first inequality holds. So you can state that as a forward reasoning step and then prove it. And then, the solution goes on to say, and, when x is non-positive, that corresponds to x being in the interval from pi over 2 to 3 pi over 2. And so I just state this in the forward direction, but perhaps this should be an if and only if, and so on. And you can sort of keep going forward and just kind of write the proof as kind of a chain of explicit assertions. And so what happens there is that, so for example, when we're in the case split where, let's see, so here's the calculation when x is positive going on. So here's the case where we're in a case split where we're assuming that cosine x is non-negative and cosine x is non-positive and cosine x is non-negative, then something holds. So we can simulate the forward reasoning solving process by just kind of stating intermediate have statements, reasoning forward. And as we split on cases, these just get get encapsulated in longer and longer lists of assumptions. Okay, and so we didn't finish the. I mean, we just got bored of kind of reasoning forward, so we stopped there. But that's one style. But the last thing I want to do, if I can just spend a couple more minutes, is talk about another way we talked about turning this into sort of a forward reasoning problem in Lean, which is rather than stated as kind of with an existential quantifier, proving that there is an answer, we sort of give the answer a name. We call it the unknown answer, and it's a definition. And from the start, we just don't, we just don't give the definition. We just put it as a sorry. And then we start to reason forward and see what we can learn. We start to try to prove that the answer is correct and see where we can get. So for example, when the proof says we shall deal with the left side of the inequality first and the right side after that, that seems to be a commitment to deciding that, okay, what we really want to do is characterize the conditions that under which the left inequality is true and characterize the conditions under which the right inequality is true. Okay. And so we're done if we can find these two characterizations and show that they characterize the left side and right side, and then provide the answer as being the set of x, where the left conditions and right conditions are both true. And we might syntactically, give the answer to be exactly this conjunction, or maybe there's even a nicer way to present it. Okay. But so if we make these steps forward, right, then we're in the case where that's what we need to do. Okay. And so, when it comes to reasoning about the left conditions and right conditions, so if we step forward, so the two things that we have to do are, reason about the left conditions and, reason about the right conditions. And so now, in the solution where you say, okay, it's clear that the left inequality is true when cosine x is non-positive, right? So that corresponds to saying, okay, we're going to do a k-split on the sine of cosine x, right? And on the left side, you can conclude that the inequality holds, and you get to the state where you've assumed that x is between 0 and 2 pi, and you've assumed that cosine is non-positive, right? And you've determined that in this case, if you're going to complete the proof, that whatever you choose to characterize your left side conditions, they have to be true in this situation. And you just bookmark this fact. And so you can write the proof going forward, then you do, other case splits and so on. And so for example, in this state, we've split on cosine x being strictly positive, and cosine 2x being non-negative. And in this case, let's see. Yeah, so we would, come to the conclusion that pi has to be equal to, x has to be equal to pi over 4, 7 pi over 4. And so the point is, as long as we've left these notions undefined, the left constraints and right constraints in the answer, we're not going to finish the proof. But if we reason forward, we can get to the point where we can see that we could solve the problem as follows. So we have to choose the unknown answer to be equal to, the set of x in the range from 0 to 2 pi, such that the left conditions and right conditions hold. And then we have these constraints. We need to know that the left conditions hold when cosine x is less than or equal to 0. We need to know that in the range from, of x that satisfy these, the left conditions hold in this case, and so on. And so on. So we get a list of constraints. And so we know that for x between 0 and 2 pi, there are no constraints at all on the right side conditions. So the idea is, the hope is that we could encourage a model to reason forward, get to this point. And now the model has more information where it can guess the right values of left side conditions, right side conditions, and the answer. So I think this is a good place. I want to make sure that I'm not taking too much time away from Melanie. So let me stop sharing now and leave it at that.
Okay, let me try to here, that worked. And now I need to make it full screen. Okay, so I just want to end to talk a little bit in the bigger picture about the context of this and why we might do it. So Alex mentioned that in, say, the IMO, about half the problems are these problems where you need to find something. So that's what I meant, to find, as opposed to just prove. You need to find an answer. And they're actually in many different kind of interesting ways. Okay, so this is the previous IMO, the 2023 IMO, and I circled in red some of these things. The find questions. So in problem 1, we're asked to determine all composite integers in and that satisfy the following property. And this starts to get at this interesting question of what does it mean to determine all composite integers in that satisfy the following property, and why is the set of n such that this property not a good answer? I think that IMO problems are designed so that there usually are not a lot of sort of an intermediate good descriptions that you would get, that there is a sort of very simple way to describe that set of integers, and then there's the problem, and there's not a lot in between, though I think with research mathematics there becomes a lot more in between. So similarly in problem 3, you're asked to determine all infinite sequences of positive integers, and unlike a question that just says, okay, find the number. If it says find the number, you could think that, okay, what you're going for is a decimal representation of a number. When we're asked to determine all infinite sequences of positive integers, it's already a hard question. I don't know if you could even formalize what would be an acceptable answer that in a way that wouldn't include the trivial answer, the trivial answer being, it's the set of sequence of positive integers with this property. All right, and you continue to have this challenge, like Alex said, about half the problems are find problems. That's true in this 2023 IMO, and here you're needing to find a function of something else. So I also just want to show that the kind of things that you're finding are changing. It's not, you can't just try to sort of, okay, understand how to find integers or subsets of the reals. There's many different kinds of sets and mathematical objects that we need to find. But my interest in this question is not just whether we can get AI to be good at the IMO. That's fun, but maybe not that important. We know how to solve all the IMO problems. But if we're thinking forward as AI a tool to help us in research math, how is it going to support that? And so I tried to take an outside audit of some of my own work to think about how often I am finding an answer or solving something versus proving something already stated, and thought about some of the different kinds of issues that come up with that. So I will sort of talk about a couple of examples. So what I did was I went through, like, I just started at the top of my webpage and went through my last 9 papers. And for each of them, I tried to classify whether the main theorem more or less was a finding and what kind of finding, or a finding problem where you have to find the answer or solve the problem versus just proving something. Okay, so in the first one, the result is something like there's a unique measure on some set of finite abelian groups with action of a group with certain moments. And the measure is, and so this is what I circled in red. So part of the claim that there is a unique measure, that of course is just a proof statement. But really the most interesting part is the part circling in red actually saying what that unique measure is. And to give you a sense, just some like little piece of the answer, you want an answer that has formulas like this. Like this is some little formula that appears in some piece of the answer. And one interesting feature of the formula is that by looking at this number on the right-hand side of this big equation, you can see that it has to be positive. All right, you don't really have to know what any of these things are, but you can see that this number has to be positive. Not the answer. I put down here some formula that comes earlier in the work towards this piece here. It's actually equivalent. But if you look just over on the right-hand side, you see it involves this alternating sum. So there's a sum with some positive signs and negative signs. And you can't tell, for example, by looking at this expression for an alternating sum that this number is necessarily positive. Later, when you manipulate it into the final answer, you can tell that it is. And so this isn't the IMO where you get like some number of points for something or not. And you could sort of have a theorem and write a paper where you stop at this answer. But what this made me think about is how often in mathematics we're not only sort of doing computations where we're doing forward reasoning, but also there isn't necessarily just one place that you could stop and say, now I have the answer, because you could stop here where you have an answer, or you could stop here where you have a more useful answer. And who knows, maybe the expressions can be simplified further into more useful forms than we did in our work. So I sort of give that as an example of like the complexity of finding an answer. Okay, and the next paper I looked at was, we sort of said the probability that an Erdős-Rényi random graph has a cyclic sample group is, and there's a number, and there's no red circle here because there was a conjecture that it was a specific number. So this was just a proof statement. But actually, that's because at some point there was a conjecture. Before there was a conjecture, there was just a question: what is this probability? And the way the conjecture came about was by a proof of this exact answer as an upper bound. And then one could conjecture, once you have that upper bound, maybe it's the answer. But that belongs to a big body of work and a type of work that mathematicians do, which might be, many questions are, you could say, of the form, prove the best upper bound possible. So you can imagine that you'd want to be able to do forward automated reasoning where you just say, prove the best upper bound you can. You don't want the system to just trivially say, give you some trivial upper bound. But mathematicians were often working in a space where you prove the best bound you can, but it's not clear that you have the answer. Maybe there is a better upper bound, but that's still a kind of big piece of the kind of work that we do. All right, let me I'll give a couple more examples. So the third paper was another kind of find where really the answer was not known for the paper, and a lot of the work was to find it. Then the next case, which was something where as the genus grows, the class of the Hurst spaces in the growth and decaying goes to, and I gave this a purple circle because in fact, we didn't even have the language to define what the answer should be necessarily when we started working on this project. So some new definitions were needed. In this case, one needs something like an Euler product in a situation where Euler products don't make sense. And this, I think, is also representative of a huge amount of mathematics research where people are trying to make definitions that will do certain kinds of things that we want them to do. And that is and sort of reasoning forward to find definitions that behave in certain ways or have certain properties is a really big piece of a lot of mathematical work. And then, okay, in the next example, the result was something like a profinite group lies in the closure of the profinite completions of three manifold groups if and only if these four conditions hold. And so those four conditions weren't conjectured before, and so they wouldn't have ever been able to be predicted. We found them only through forward reasoning, and also you never possibly could have predefined some set of acceptance. I should have said acceptable answers. I mean, in some ways, you could say that, wait, four conditions is more complicated than the original question. The original question, you could just say it's the closure of the profinite completions of three manifold groups. Like, why do you need four conditions when there's just one? But these, the conditions sort of help relate it to something. And so anyway, so this is just a little bit of me thinking about what kinds of things we do in mathematics, especially when we're forward reasoning. And one of my big takeaways is that it's often not clear when we're done. There is no actual clear done. I mean, at some point we write a paper, but it's not like, well, okay, once you have just an interval of real numbers, okay, then you're done, in the way that you might in this one IMO problem we formalize, sort of be able to really define what it means to have an acceptable description of the set. I think many times in mathematics, we are trying to come up with better and better descriptions of a set, and there's not a kind of unique best one. And, I bring this in just because I think as we try to think about how we might use AI with Lean to do forward reasoning, I want us to think about it in the context of what will ultimately build something that will support mathematics research. And I think that IMO problems are a great place to get started in how they're difficult and require some ideas. But I want to think about also what we do if we can build it to support the different kinds of like finding or prove the best upper bound you can style problems, or come up with a definition that does certain things that a lot of mathematics, that a lot of mathematics research entails.
Conclusion, or that's the summation of your talks?
Sorry, was that a question?
It is. It was a great talk from all four of you. Should we allow somebody to conclude and summarize, or is that we'll go out on that note and ask questions?
I can do a quick recap. So Amaury, started by just giving an overview of the neurosymbolic combination of sort of using a system with lean and machine learning. Alex described the success of such an approach with IMO problems, but raised what the four of us think is a really interesting problem of how you can use the setup not just to prove theorems, but to solve problems and find solution to problems. I tried to, describe some of our initial discussions in that direction. And I think Melanie did a great job of giving a sense of why this is really fundamental. I mean, this isn't just kind of a one-off IMO problem thing. This is really fundamental to mathematics, that, mathematics isn't just about proving theorems. It's about finding theorems and finding solutions. And so, yeah, there's a lot to do, but I think we're excited about it.
Okay, well, thanks, Jeremy. Excellent. Let's start. That's a great talk. Let me just say that was there were a number of activities on the theorem proving week of our program, and this was a collaboration which really formed at that week, and you can kind of get a sense of the types of discussions that we had during the program.